Hello everyone, my name is Istaq Mahmood, and in this short presentation, I will give an overview of our course project and clearly explain my individual contribution. I would like to mention briefly that during the original team presentation recording, I was traveling to my home country and had very limited internet access, so I could not present live or record with the team. This recording is to explain my role and contribution to the project. Our project is titled Emerging Threats in V2V AI-Driven Cyber Resilient Platoon Network. The main goal of this project is to design and implement a secure hardware-based testbed for autonomous vehicle platooning with a focus on detecting and mitigating physical layer jamming attacks. In our team, Shadman handled hardware-software integration. Mohammed focused on RF jamming implementation and performance evaluation. My role was AI and machine learning for jammer detection, along with data engineering, feature extraction, model training, and performance analysis. Autonomous vehicle platooning depends on continuous B2B communication in the 5.9 GHz band, while cryptographic security protects the data content. It does not protect communication availability. A smart jammer can exploit this by injecting wideband noise, which reduces the SNR below the decoding threshold. This leads to denial of service and creates serious safety risks such as loss of coordination or vehicle collisions. This slide shows our system architecture and hardware in the loop testbed. Instead of relying on simulations like MATLAB, we built a real physical setup. We use user B210 radios as V2B transceivers with Raspberry Pi 5 and laptops handling edge signal processing. The entire system runs on GNU Radio Companion under Linux. This setup allows us to test jamming attacks and detection of different realistic methods or real-world conditions rather than purely simulated environments. This slide explains how we implemented the jammer. We configured a dedicated USRP node to act as a man-in-the-middle attacker. The jammer injects wideband Gaussian noise in the center frequency, effectively flooding the channel. As a result, we observed immediate constellation diagram distortion and significant packet loss at the receiver. The spectrogram on the right confirms um, high powers, you know, high power saturation across the target bandwidth, validating the effectiveness of the jamming attack. We extracted both raw and engineered features from the hardware signals, including signal power, noise power, RSSI, peak power, and power variance. From these, we derived SNR and SINR in both GB and linear scales to better capture link degradation caused by jamming and improve machine learning accuracy. For data engineering, we did not rely only on raw hardware measurements. We extracted signal power and noise power directly from the radios, then engineered higher level features such as SNR in dB and SINR in linear scale to better represent link quality under jamming. This feature engineering significantly reduces model convergence time and improved detection accuracy on edge hardware. The scatter plot matrix shows clear separation between benign and jammer samples across key features such as signal power, noise power, SNR, and SINR. The jammer introduces higher noise and lower SNR or SINR, creating distinct patterns that make the classes well separable for machine learning models. We trained and evaluated multiple machine learning models, including logistic regression, SVM, random forest, gradient boosting, CNN, and neural network to accurately classify benign and jamming scenarios. This slide compares training and testing F1 scores as the dataset size increases for different machine learning models. The results show stable generalization with minimal overfitting, indicating reliable jammer detection performance. These configuration matrices compare how accurately each model classifies benign and jamming signals. Tree-based models and neural networks achieves high true positive rates while keeping false alarms low. Here we integrate the trained machine learning model directly into the GNU radio signal processing chain. The system computes features in real time and outputs a jamming detection decision every 100 milliseconds on edge hardware. The system successfully detects jamming in real time, which is now complete. We are currently implementing frequency hopping spread spectrum so the radio can automatically switch channels when jamming is detected. In conclusion, we built a self-defending V2V radio system that detects and responds to physical layer jamming attacks. The key novelty lies on hardware, real hardware validation, its native AI execution, and cost-effective design suitable for low-cost platforms like Raspberry Pi. That's all about our project. Thank you so much.